Let's imagine that we have a pulley. A pulley is like a wheel that can spin. And this pulley is attached to, let's see, the ceiling up above. Now we take a string and put it over the pulley. So we've got a string that goes up one side, around the pulley, and then back down the other side. And on the two ends of the string, we attach two masses. So let's say we attach a mass M1 on one side of the string and a mass M2 on the other side of the string. If these two masses are equal, they'll just stay there and they won't move. But let's assume that M2 is larger than M1. If M2 is larger than M1, then the force pulling down on M1 will be larger than the force pulling, the force pulling down on M2 will be larger than the force pulling down on M1, and what's going to happen? Well, M2 will go down and M1 will go up. Well, let's see if we can figure out what kind of motion, what kind of acceleration these masses will have. We have the forces acting on the objects are the tension in the string, and on M1 the tension in the string will pull it up, and on M2 the tension in the string will pull it up. And one approximation we're going to make is we'll assume that the tension is the same. That is basically assuming that there's no friction in the wheel, no friction in the pulley, and that the pulley is massless. In other words, there's no force acting on the two sides of the pulley that we need to worry about, that the pulley can accelerate up or slow down without any force. It's basically assuming there's no friction and a massless pulley. We also have a force pulling down on M1 with M1G, a force pulling down on M2 with M2G. We've got two objects, M1 and M2, and we've got to look at them separately. What's going to happen? We have assumed that M2 is greater than M1, so we are assuming that M2 is going to go down and M1 is going to go up. But whatever acceleration M2 has down, M2 will have the same acceleration up. If M2 goes down 1 meter, M1 must go up 1 meter. We're assuming the string is not stretching. So we'll assume that M2 has an acceleration down of A, and M1 has an acceleration up of A. Well, because M1 is going up, we'll define upward as positive for M1, and because M2 is going downward we'll define downward as positive for M2. So what kind of forces do we have in terms of Newton's second law for these two objects? For M2, if downward is positive, we have M2G acting in the positive direction, and then the tension in the negative direction, so minus T, and that must equal M2 times A. F equals MA for M2. What about for M1? The forces on M1 are T in the positive direction, so we have T, minus M1G in the negative direction, minus M1G, and that must equal M1A for M1. Now we've got two equations with a whole bunch of unknowns. Well, let's assume that we know the masses. We'll assume that whatever the values are for the masses, M1 and M2, we know those. What do we not know? Well, in these equations, we don't know T, the tension, and we don't know A. We have two equations with two unknowns. Mathematically, in general, we know we can solve those. If you've got two equations, you can solve them for two unknowns. How are we going to go about doing it? The easiest way to solve these is to add these equations together. Because we've got a minus t and a plus t, the t will then cancel, and we'll have a single equation that we can solve for A. Once we have that, we can put it back into one of those equations and solve it for t. Well, I'll do that and I'll be right back. Here I have added the two equations together. So on the left side I have M2G minus t, and then plus t minus M1G. And then add the right sides together and I have M2A plus M1A. Now notice I have a minus t and a plus t, and they cancel out. We're left with, on the right side, kind of switching both sides, factoring out A, I have A times M2 plus M1. And on the right side, we've got M2G minus M1G, factoring out G, I have M2 minus M1 times G. Divide both sides by m2 plus m1, and I have A equals m2 minus m1 divided by m2 plus m1 times g. And there we've got a solution for the acceleration in terms of the masses, m1 and m2, and g. We can then take this result for A, stick this equation in here, in either one actually, and then solve that equation for t. I did that and I got this result. It's got a little bit of algebra in it. I won't put it up, but if you're interested, I definitely suggest that you give it a try. What you should get then is that t is equal to 2m1 m2 divided by m2 plus m1, the whole thing times g. And there we go. There is our solutions for this problem. One thing I'd like to do is something that's very, very useful. And that is, let's think about this equation for the acceleration. Let's ask ourselves, does that make sense? Does that seem like a reasonable result? Well, it's got these masses all over the place. Who knows? Who knows if that's correct or not? One way that you can look at an equation and try and determine if it makes sense or not is to look at what it tells you in certain extreme situations. For example, what if m1 and m2 are the same? What if they're equal masses? What do we expect to happen? You have equal masses on both sides of the pulley. What's it going to do? Well, it's not going to move. It's not going to accelerate at all. Well, what happens with our equation if we put m1 equals m2? If m2 and m1 are the same, what's m2 minus m1? It's 0, and we get 0 acceleration. Well, that's exactly what we just said. So that makes sense. Having this factor of m2 minus m1, it makes sense that we have that because that gives us a 0 acceleration when the masses are equal. What if we said m2 was bigger than m1? What if m2 were much bigger than m1? Much, much bigger. What if, rather than being similar to each other, what if m2 were 1 billion kilograms and m1 was 1 milligram? Okay, some extreme situation. Well, then the fact that m1 is here would have basically, or very, very little effect on m2. What would m2 do? It would accelerate downward at what acceleration? At g. We would expect it to accelerate at g just like it were in free fall. The fact that m1 was attached to it would have practically no effect. Well, what do we get in that case? If m2 is much, much larger than m1, what is m2 minus m1? Well, it's basically m2. What is m2 plus m1? Again, it's basically m2. What is m2 over m2? It's 1. And what is 1 times g? It's g. So we get an acceleration that's equal to g, and that makes sense. That's exactly what we just thought. So I wanted to point that out because sometimes if you get an equation, even though it might look very, very complicated, if you think about it, it's in certain extreme situations. Maybe if it's dealing with masses, what happens if you have equal masses? What happens if one mass is much, much larger than the other? What do you get in those situations? Then you might see, oh, that makes sense, that makes sense, that makes sense. It might help you understand what an equation is actually telling you. Very, very good. I hope that made sense, and I hope you enjoyed that. Next time, we're going to start looking at some different applications of Newton's laws. We're going to use them to develop another way of solving problems. Hope you enjoyed it. See you next time.